The idea is to give you a brief overview of what is the science of tropical cyclone in a changing climate. What do we do for the evaluation of tropical cyclone changes in the current climate, and what we do expect for the future, and whatever. A few words about the center where I come from. I'm from the Euro-Mediterranean Center on Climate Change. This is a research center that was born almost, I would say, 12 years ago. And the aim of the center is to investigate the climate variability and change, and to provide reliable information for policymakers and stakeholders of different sectors. The center is distributed in 9 different divisions, research divisions. There are people working on the physical side, oceanographers, atmospheric people, people working on sea ice, and so on. So there are 3 divisions that are mainly devoted to this kind of analysis, but we also have people working on the economic side. We have 2 divisions working on economy, and we also have people working on impact, on agriculture and fisheries and whatever. As I said, I'm from the physical side. I'm from the climate simulation and prediction division, this one here. What do we do in this division is to investigate the variability of the climate in many different aspects. I'm involved in the analysis of extreme events such as tropical cyclones, but we are also interested in different time scale. We have people working on seasonal projection, seasonal forecast, decadal forecast, and long-term projection. Our main tool are general circulation models, typically fully coupled general circulation model, and we are going to talk about this kind of tool during this talk today. So this is the outline. First, a brief introduction on tropical cyclones. So what is the process, and just few information on the distribution in the globe of this kind of atmospheric events, and then just few words on the economic on the economic implication behind, and then we will go to the central part of the talk, so the interaction of the tropical cyclone with the climate system in both directions. So how the climate system affect the tropical cyclone activity, and how tropical cyclones tends to affect the climate itself. And then finally, we are going to talk about the future projection of tropical cyclone activity in terms of different aspects and the impact and so on. So let's start with the first part on tropical cyclones. I assume that you have already heard about tropical cyclones. These are typical natural destructive events, and they are somehow convective organized structures, typically happening along the tropics, because there are some conditions that must be respected. Since they get their energy from the ocean, they need to be over a warm ocean, so typically they develop over the tropical region. So the fuel is the energy coming from the ocean, and then they also need an atmospheric condition that is particularly unstable, that tends to facilitate the upward motion of the parcels of the air. We have to be not too close to the equator, because this mass of air that tends to come to converge to the sea level pressure minimum typically we have when a tropical cyclone starts to develop, we need to have a sort of force that tend to deviate this mass of air that are converging, and this force is the Coriolis force, and the Coriolis force is something that is strongly related to the latitude. Is 0 at the equator, so we cannot have any kind of cyclonic structure burning at the equator, so we need to be at a little bit higher, so a few thousand kilometers north or south of the equator, to have the development of this structure that start to rotate and to get energy from the ocean. And this is something that is important to know. This is the reason why you won't see tropical cyclone along the equator, but the idea is, so why? Well, since we have the Coriolis force that is increasing with latitude, why don't we have tropical cyclone at the poles? That's because the other condition, that is a sufficiently warm ocean, is not present in the poles. So there is this band along the tropics that facilitate the development of the tropical cyclones. They also need a sufficiently low wind shear, so you don't have, if you have a high difference in the velocity of the wind in the upper layers of the atmosphere and in the lower layer of the atmosphere, this tends to destroy the towers, and there is no possibility to build the tropical cyclone itself. So these are the typical conditions that we need. Depending on the basin where they develop, they assume different names, and typically when the tropical cyclone reaches a velocity of 33 meters per second, that is something like 110 kilometers per hour, the wind velocity at the surface at 10 meters is the parameter used to classify the tropical cyclones, so that they became hurricane or typhoons, depending on the region where they are. Hurricane and typhoon is the same process. They are called hurricanes around the US, typhoons in the West North Pacific, and they are called intense cyclones in the Southern Hemisphere. So hurricanes and typhoon are intense tropical cyclones, okay? There are different classes associated to tropical cyclones. This is the Saffir-Simpson scale, where they are classified by intensity, so by wind velocity at the surface. In the past, also the sea level minimum pressure was used to classify hurricanes. That is not used anymore. Now we just focus on the wind velocity at the surface. And when you have wind surface velocity higher than 60 meters per second, you can claim major hurricane, category 4 and 5. We are somewhere here, okay? This is the schematic representation of the tropical cyclone itself. In the upper left panel, you see the wind speed vertical section. You can see that the maximum value are expected close to the surface. And if you take a look at the same scheme, but for the temperature, you can see the very well-known warm core in the upper level of the atmosphere. This is something that is created by the heat released by the parcels that condensate and precipitate. So this is something that we can call the engine of the tropical cyclone, because this is facilitating the upward motion of the parcel coming from below, so bringing the energy that you had at the surface in the upper layers. The structure is typically this one. You can see here that you have the high that is relatively calm region that is 20-40 kilometers wide. And then you have the high wall where you have the maximum precipitation associated, and then the spiral rain bands that can go far, also 1,000 kilometers far from the high of the tropical storm. So this is just to give you an idea of the dimension of the tropical cyclone. The smallest one has been found, if I remember well, when I was born, in 1974, yes, December, and it was something really, really small with respect to the typical tropical cyclone. It was 50 kilometers wide, but then you can also have tropical cyclones that are 1,000 kilometers wide. The biggest one was a typhoon Tip in 1979, it was 2,000 kilometers wide. It was really huge. You can see that in few days, this kind of structure can spawn the entire US continent, just to give you an idea of the dimension. So we are talking about something that is really huge. You know that there are other cyclonic processes, the famous tornado, but this is a completely different thing. Tornadoes are really small, and even with even higher winds associated than this one, but it is something that is confined in a few hundred of meters. We are talking about processes happening in a 2,000 kilometer wide domain. Typically, we have something like 90 tropical cyclones per year at the global scale. There is an internal variability, but the average number per year is 90. They are mainly concentrated in the West North Pacific, this region here, but also in the East North Pacific, the Atlantic region, and in the Southern basin. The color here indicates the most intense. Red means intense, Cat 5. And as you can see, you can extrapolate from here. The Northwest Pacific is also the region where we have the most intense typhoons, because we are in the West North Pacific. These are hurricanes, these are typhoons. The seasonality of the events in the two hemispheres is shown here. In the northern hemisphere, where we also have more tropical cyclones, we have the maximum, the season starts in June and ends in November, December. In the southern hemisphere, on the other hand, you start the season in October and it ends in March, April. So if we focus for a second on the northern, on the Atlantic basin, this basin here, and we take a look at the return period of the most intense tropical cyclone, you can see that the southern part is the most affected. Going north, you have less probability to be eaten by the strong tropical cyclone. And if you look at the time series, these are numbers representing the total tropical cyclone, yellow, hurricanes, red, and super hurricanes, so category 3 and 5, the purple numbers here. If I can't read, but I think that this is something 150 years time series. You can see that there are no huge changes in the number of tropical cyclones, but if you focus on the most intense ones, something seems to be happening in the last period. So it seems that we are starting to have more intense tropical cyclones. And this is something that we will investigate a bit more also in terms of projection based on our result coming from general circulation models. So we said that the most intense tropical cyclones are called hurricanes and typhoons, but the relative destructive effects are related mainly to three. There are more than three, but the main three factors are strong winds, storm surge, and extreme precipitation. This is responsible for billions of dollars of damages and a huge number of deaths in the years, and we will be back on this in few slides. But if you want to take a look at the single factors, starting from the strong wind, we can say that typically what we do expect from strong wind is that they tend to remove the roofs from the buildings and so on. There is a Bernoulli effect related to the reduced pressure in the upper part of the roofs by the winds, and the tendency to the roof to be removed. And also there is a local effect that is more important than what we expect from the sustained wind, because an hurricane with a sustained wind of, let's say, 50 meters per second, as associated, depending on the topography and depending on the region where you are and depending on the local circulation that can be developed, you can have also changes in the direction and in the intensity of this mean flow. So you can have stronger gusts over certain region, changing the direction, and this is something that plays a role more important than the sustained wind on the buildings and create and destroy everything around. These are typical examples of damages from winds. These are from an hurricane we had 2 years ago. I forgot the name. This is an old hurricane in the 70s. But I mean, typically the damages from the winds are local and covering just part of the total amount of damages that we can see at the end of the hurricane. The second one we mentioned is the storm surge. The strong winds associated with tropical cyclone tend to push the water into the shore, and this is somehow leading to floods along the coast. What we can have is typically the worst situation is the combination of this water that is going inland associated to the normal tide in the region, and in this case you are creating a storm tide, putting together the storm surge with the normal tide, and this is something that can lead some time somewhere to increasing the sea level, coastal sea level of also 5 meters. 5 meters is huge. If you take a look at the the effect for instance, if you take a look at the city after the Katrina passed, you can see that there are, if you walk around New Orleans, you can see that the line of the water is somewhere at the second floor. There is a line around many buildings that indicates where the water was after the landfall of the Hurricane Katrina. And this is really evident for some of the tropical cyclones we had in the recent past. Another factor is the extreme precipitation associated with the tropical cyclones and the related floods. Typically, people think that stronger to sea, strong means with higher winds, is associated with more precipitation. This is not true. The precipitation is something that is mainly the amount of water that reaches the surface is mainly related to the time that the cyclone spend over a region. You can also have just a Cat 1 tropical cyclone. It is the case of Allison in 2001 that was not moving that fast. It was hovering over Texas City, if I remember well. And even if it was a Cat 1 hurricane, it released a huge amount of water over the region because it was staying there and pushing the water over the land and accumulating. So typically, most of the damages from the precipitation are not along the coast, but are inland when the tropical cyclones start to stay, to do not move before their disappearance because they do not have the fuel coming from the ocean. And so you can have different floods, flash flood, urban floods. These are similar events, just different in terms of the severity of the event. And also, typically, the river tends to accumulate the water that is coming from the catchment basin of the river during the precipitation, the extreme precipitation period associated with the tropical cyclone. And then at a certain point, they start to collect the water, and when you reach the higher level, you can have over a certain region really important floods. Even few days later, the maximum intensity reached by the tropical cyclone. This is a typical effect that you can have. You can see these are the roofs. These are 3 or 4 meters high buildings that are completely covered by water. So different effects: strong winds, storm surge, extreme precipitation. These are participating to the total number of deaths we had due to tropical cyclones, so both hurricanes and typhoons. Storm surge is the main cause. The rainfall is something similar. We are talking about 50 and 30%. The winds are responsible for no more than 8% of the deaths associated to tropical cyclones. And there are also other small contributions that are, for instance, the ones here, surf and offshore, are related to the activity over the sea in the region. I mean, people swimming or sailing or whatever just before the event. And also tornado, the one we mentioned before. We have to be clear that these are not the typical tornado you have in the Great Plains. These are smaller processes that develops on the back of the typhoon, but they can still create huge damages. So moving to the damages, I just collected some information mainly related to the US. This is also because this is true for everything, not only for the numbers related to the economy, but also for the number related to the physics, to the data you can use to validate your model, or whatever related to hurricanes and typhoons. If you go to the conference, to the hurricane conference around the world, you can see that 80% of the talks are on hurricanes, US, and 20% are on East Pacific or Northwest Pacific or Asia domain. So the most of the information we have is in terms of economy or climate fields, whatever, is on the US side. This is not that good, but this is what we are living in the community. So if you take a look at the list of the, I don't know if you can read these numbers. This in the left table here, you have the list of the ranking of the most the tropical cyclone with the higher impact. I mean, in terms of number of deaths, in the first 5, you can see that more than 1,000 deaths per each tropical cyclone is found. There are tropical cyclones that in the past registered even more than 5,000 deaths associated, and these numbers are somehow divided in the contribution we have seen before: winds, floods, or extreme storm surge. And also, if you take a look at the money, so the associated damage in terms of US dollars, you can see that the list is a bit different. And this list, there are elements that are reaching something like 125, and this number is even higher. It has been recomputed recently. For the Hurricane Katrina is $160 billion, the cost of the damages associated to the Katrina hurricane. And this list is updated every year, not only in terms of new events, but also in terms of different way to compute the damages. That is also another part of the development of the people working on tropical cyclone and economy. So, for instance, if this was the list last year, if you take a look at the list this year, they changed it, and if I remember well now, the Katrina hurricane is to Katrina they associate 160 billion instead of 120 billion as the cost. So Katrina still remains the most devastating and costly hurricane in the history. But another important thing to say, and is that if you take a look at the cost per year, the 2005, that was the year when we had the Hurricane Katrina, is not the most costly. The 2017, 2 years ago, we had a series of hurricanes. The most intense was the Harvey, and Harvey was really huge, also in terms of costs, and the cost is something like 125 billion itself, less than Katrina. But if you put Harvey together with the other events, we had more than 10 events eating the cost during that year, and if you put them together, the cost reached $300 billion for a single year. So these costs are somehow averaged per year in a number that is around 50 billions. These are still costs for the US. 50 billion per year is the cost associated to tropical cyclone, and this is distributed non-uniformly along the different sectors. For instance, most of them is on the residential sector, this one, and then there is a fraction that is on the commercial sector, and then the public sector is the less affected. Also, in terms of compensation of these losses, not only the insurances are playing a role, but also directly the local state or the US government is providing money to compensate these damages. An interesting study that has been done a few years ago showed how, for the different regions, here you can see the Central America, the Eastern Asia, North Africa, so this is Mozambique or something like that, Northern America and other region of the globe. You can see in blue the cost still US dollar billions, millions in this case, sorry, per year. And the blue represent the present cost. The red represent the future cost for the end of the century, but without the climate change signal associated. So this is the difference just induced by projected changes in the income of the people in the different number of people that is projected to live along the coast, and so on. So this is not a number related to climate change effect on tropical cyclones. This is an interesting plot from my point of view, because without anything, we do expect in the Western Pacific, the region where we have the maximum effect, also in the North America here, we expect almost doubling the cost associated to the tropical cyclone. And in the Eastern Asia, this is Western Pacific, we expect even more than doubling the cost without climate change signal associated. So we know that tropical cyclones are affected by changes in the climate conditions. So we also know that the climate is projected to change. So what about this plot putting together also the contribute of the climate change? How can we consider the climate change effect in terms of changes of the activity of tropical cyclones? So what we can use, there are different tools, but the most useful one are general circulation model. You have seen many results in previous talks mentioning couple model intercomparison project 5, couple model intercomparison project 3. These are all couple model intercomparison project that provides data and numbers for the past and for the future to the IPCC for the preparation of their report, assessment report, every 10 years or whatever. General circulation models are the tool at the base of this kind of process. And we are going to talk about general circulation model now and how tropical cyclones are represented in this kind of tools. But I would like to start from the beginning. General circulation model started, the evolution of the concept started at the beginning of the past century. These guys at the beginning of the past century said that, well, based on some assumption on past maps, yesterday sea level pressure maps and temperature and whatever, looking at the time series we have in the past, we could somehow derive the future result. We could derive what we can expect for tomorrow or past tomorrow. It was the first empirical approach to the forecast. Then in 20 years, these other scientists, Lewis Richardson, made one step more. He suggested that based on some equation that are these are the famous partial differential equation known as the primitive equation, the climate equation, it should be possible to derive the time evolution of the parameters that determine our weather system. So he derived his system, he prepared his theory, he said that it was possible to say something about the next 6 hours. So he made the first 6-hour forecast. In order to do that, he spent 6 weeks working, counting, and whatever, no computer at that time. He spent 6 weeks to forecast 6 hours. So it's something not that efficient. And also he got a completely wrong solution. But this was the first step in terms of numerical approach to derive future climate, future weather, and then climate conditions. So what we have in our models now is this kind of equation computed for each grid point we consider in our model, evolving in time. And so the step that was necessary in the middle, at the end of the past century, was the increase of the computational power to make the huge effort of counts you are supposed to do to compute this kind of equation. So at the end, the higher is the resolution of the model, so the higher is the number of grid points you have, the higher is the possibility to resolve small processes. So the higher is the possibility to be close to the observation, the higher is the cost of you have behind the numerical model for the computation. Because if you want to be close to the real representation, you need to have a resolution that is as much as possible close to 0. I mean, the resolution is important not only in terms of horizontal resolution, but also in terms of vertical resolution, especially for the representation of processes like the tropical cyclones and the hurricanes, the one we are talking about. And also, based on the different resolution of the model, if you just have models with 1,000 kilometer grid box resolution, that is what we had in the 80s, 40 years ago, no more than that. In the 80s, the single grid box of a general circulation model was 1,000 kilometer. You have no way to represent processes like tropical cyclones in such kind of models. You can just look at planetary waves or something like that. On the other hand, if you go to 1 kilometer, less than 1 kilometer resolution, you can reach, you can represent also the cumulative convection, and really small scale processes really important. If you take a look at the evolution of the horizontal resolution in the past 40 years, this is what we use. This is the representation of the European domain in the first assessment report of the EPCC in the 1990. This was the Europe. You cannot see the Italian domain. And this is what we had in the second assessment report, in the third one, in the assessment report number 4, that was in 2007, we started to have something reasonably comparable to the orographic feature over the region. And then in the fifth assessment report, the resolution increased a bit. This is something average over the model. Not all of the model involved in the CMIP have the same resolution. This is the average. And well, so this is the typical resolution. No, not the typical. This is the higher resolution you had in the assessment report 5. So CMIP-5 result, the one you have seen, even in the previous talk, uses AR5 result, so from the CMIP-5 experiment, and this is one of the highest resolution model present, that was something like 80 kilometer for each grid box. Now we are moving to CMIP-6. Maybe many of you are already aware of CMIP-6. CMIP-6 is coming. We are working, the different modeling group around the world are working for the provision of the data from their own models. We are, as EMCC, we are participating with more than one model. And I want to say you that the average resolution is not that different from this one. You cannot expect big improvement for CMIP-6 at all for the projection. But within CMIP-6, there is also a small MIP that is the IRS MIP, where few centers are participating, where just few scenarios are presented, not the whole possible matrix of scenarios, with a resolution that is of the order of 1/4 of a degree. So we are going to have 0.25, that is something like 25 kilometer resolution result within CMIP-6. And this is very important for, I would say, for my research, because at this resolution, we are able to represent category 5 hurricane and typhoon. This is the first time. With this kind of resolution, we just had Cat 1. So in CMIP-5, you can only 5 hurricanes represented as Cat 1. Few of them, category 1. The most intense category 5 are now represented in the new version of the models with 25 kilometer of horizontal resolution. So this is a huge step for the hurricane science, for the hurricane study in the future climate, and so on. So with different groups around the US and Australia, we are working on these models to investigate the effect of the hurricanes on climate and whatever, and the opposite. So we now have a really improved tool with respect to a few years ago. Together with the evolution of the horizontal resolution in the general circulation model, we also had an increase in the complexity of the system. At the beginning, we just have, in the 70s, we just had atmospheric model. Then we started to have atmospheric and ocean model, different group developing their own general circulation model on the atmosphere and on the ocean. And then people working on general circulation model for the sea ice. And then in the 90s, we started to put things together. This is a huge step for the science of hurricane, because we started to couple the atmosphere and the ocean. And the signature of the hurricane in the climate system is mainly through the interaction with the ocean. So having the interface active, having the exchange of the fluxes, having the exchange of the max heat and momentum fluxes active in a general circulation model, together with the provision of the possibility to perform future climate projection, because you don't need any boundary condition to run it. It is a self-consistent system just digesting information about the radiative forcing, the carbon dioxide changes and so on. You also have, this is one thing, and the second thing is that you can represent really the interaction between the atmosphere and the ocean with the coupled system. And this is of huge importance for the science of hurricanes. Here you have the representation of how our full system, the last version of the CMCC CM2 model. There are many components: PIs, river routing, atmospheric model, ocean model, land and vegetation model. The resolution, we have different versions, and the higher resolution is at a quarter degree, both in the ocean and in the atmosphere. And this is the one we use to participate to the IRIS map I have shown you before, participating to the CMCC-IV. As I said before, a huge amount of computational power is necessary to run this kind of experiment. This is our previous, because we changed it 1 month ago, computing system at CMCC. Climate sciences are the most expensive sciences in terms of computational power. You need to upgrade your system every 2 or 3 or 4 years, and you have to because typically you want to run higher resolution simulation, and if you want to maintain the number of years simulated for each CMAP, you need to improve the computational power you have available. We started in 2008 to the CMCC-III, and then we went to CMCC-V in 2013 with these 3 models. And then we are now in the 4th of CMCC-VI with this 4 version of the model, different resolution. But just to give you an idea, with 1,000 CPUs, it is not that much, but 1,000 CPUs, to run 1 year of simulation, I need 1 day in our supercomputer. That means that if I want to spin up my model before running future scenario, if I want to have a stable model, coupled system that is realistically similar to the observation of the observed world, I need to run it for, let's say, 500 years in present climate condition. And then I can run the historical period, and then I can run the scenarios. It means that I'm going to run thousands of years. 1,000 of years, 1 year per day means 3-4 years of simulation with 1,000 CPU dedicated to this process. So what you can do is to use more than 1,000 CPU. You can increase the power of each CPU or whatever, but this is not that cheap. Anyway, general circulation model in CMCC-III started to be able to represent structures similar to tropical cyclone. We didn't have category 1 typhoon or hurricane, just small, less intense structures. But then going to the CMCC-V, we had the category 1 typhoon, and then category 5 in the last version of the model at 1/4 degree at 25 kilometers. Also the spatial distribution of these are the genesis point in the observation, and these are the genesis point in one of our models. You can see that they are reasonably well in agreement over a 30-year period. We still have these ghosts here. Can you see? These are tropical cyclones we have in the model that are not in the real world. This is mainly because we still have, and also many other groups still have a warm bias over this region and a negative bias in the vertical we share over this region. But in general, we have a right number of species in the main basins. Also, the representation of the structure is somehow realistic. This is what we have in CMCC-V, and this is what we have in CMCC-VI. In CMCC-V, the high in the wind was present, but not in the precipitation. Now we have the high in both winds and precipitation, with also different numbers associated, because now we are able to represent the most intense one. So, general circulation model in general circulation model, tropical cyclone can develop. The counting is reasonable, the intensity of the storms is reasonable, and also the relationship between the climate variation and the tropical cyclone formation is reasonable, both in terms of dependency of El Niño Southern Oscillation, Northern June Oscillation. So general circulation model are able to represent the main relationship between the climate and the tropical cyclone activity. For instance, recently also we found a relationship between the subsource surface in the eastern part of the Atlantic and the genesis of a tropical cyclone in the main development region in the Atlantic basin, and the description of this process has been possible thanks to general circulation model, because thanks to general circulation model we can have sufficiently higher frequency data to investigate both for the atmosphere and for the ocean, to provide us the information to better understand the mechanisms behind this sort of teleconnection shown here. So this is the time evolution of typhoon twins. These are two typhoons developing in the West North Pacific in a quarter-degree resolution model. You can see the sea level pressure in this panel, the wind, and the sea surface temperature here. So the right one, this one, is the one that at a certain point reaches the category, the higher category, the category 5. It starts to be cat 1, 2, yellow, orange, and then at a certain point it is category 5. Associated to this one, let's focus on this one, forget the other one. If you take a look at the evolution, this is the minimum pressure in contour. In the sea surface temperature pattern, you can see that at a certain point you start to have a wake. This is a wake that is induced by the tropical cyclone due to the divergence of the water induced at the surface that is somehow calling water from below. The water in the deeper layers is cooler than at the surface. So the tropical cyclone activity tends to recall cold water from below. And this has an effect at the surface that is reducing the fueling of the tropical cyclone itself. So this is a negative feedback. A strong tropical cyclone induced upward motion of the water that is somehow cooling the surface. The cooling of the surface is reducing the tropical cyclone intensity itself. If the cyclone is moving fast, who cares? The wake stay back. If the cyclone is moving slow, the self-inducing weakening is really effective. And this is something that we can represent in our couple models, general circulation model of the atmosphere of the ocean with high frequency coupling. If you run the same model with a coupling frequency of the order of 1 day instead of the order of 1 hour, you completely lose the signal. And if you completely lose the signal, you can also have a representation of the intensity of the cyclone that is 1 order of magnitude wrong. This is because the real effect, the feedback with the ocean, is important for a right representation of the tropical cyclone itself. So this is saying us two things. The first one is that this number, this cooling of the order of 5 degrees, that is similar to what we have observed in the real world, is well represented by the model, and this is a good thing for the tropical cyclone representation itself. But also that this tool gives us the possibility to investigate the effect of the tropical cyclones into the ocean. And the effect of the tropical cyclone into the ocean are the effects that we do expect that will remain in the climate system, leaving a signature in the climate average conditions. So thanks to this ability, we can also take a look at the effect of the tropical cyclone on the climate system itself. These are composite over on the sea level pressure and on the surface wind associated to the most intense tropical cyclones in the Western Pacific. You see this huge, big negative anomaly in sea level pressure that is the result of the whole tropical cyclone happening here, and this is what we call the tropical composite cyclone over the region. Associated to this minimum in the region, you also have Negative anomaly in the upper part of the tropics induced in the winds, and this is the U component of the wind, the zonal component of the winds, and positive anomaly in the southern parts of the tropics. This is the composite effect of the tropical cyclone, because in this region here, they tend to neglect each other, but the net effect is the one you see here. And this is something that is leaving a signature in the ocean, also in terms of heat transport. If you take a look at the ocean heat transport, this is the latitude, this is the ocean heat transport in petawatt. You can see that the anomaly induced by the cyclones is positive northward of 20 degrees, and 20 degrees was the point where we had the maximum genesis, number of genesis, and negative southward of this number here. So tropical cyclone activity is affecting the oceanic transport and also the average heat content over the tropical domain. There are also other effects, remote effects. For instance, here you have the representation of the effect. This is a paper that we had in 2012, if I remember well, where we found a connection with the Arctic sea ice diminishing during season when in the Atlantic you have a strong activity in the tropical cyclone. This is something that we related to the excitation of Rossby waves induced by the tropical activity or by the tropical cyclones in the tropical region, that is somehow playing a role in modulating the sea level pressure at higher latitude, that in turn affect the sea ice melting over the region. So our system is really complex. Tropical cyclones are playing a role, and the tool we have, general circulation model, help us in the definition of and also in the quantification of these mutual effects. What we do expect for the future? When we talk about future, we talk about projection. So we never say that we predict something on a long time scale. What we do is to project different conditions in a future period. Typically, we go to the end of the current century with our projection. But the typical difference between a forecast and a projection is that a forecast is mainly related to the initial condition you have. So it is an initial value problem. It is really important, a good representation of the actual state before starting the forecast in the next few days or weeks. When you move to the long-term projection, you are starting to talk about a boundary value problem. You can compare the statistic of a future period with the statistic of the present period. You cannot say that we are going to expect a higher temperature of the Pacific the 12th of July in 80 years from now. You cannot say this. You can only say that the statistics, you can only investigate how the statistic of the last 30 years of the current century are going to change with respect to the statistic of the current climate. So this is what we can do with projection. You cannot do something that is a forecast, but just you can compare results under different conditions in terms of radiative forcing. Why I said radiative forcing? Because typically a future scenario is a plausible series of number representative of the concentration of the different gases that are playing a role in determining the radiative surface balance of our planet, that are somehow derived by what we do expect in terms of population growth, changes in the energy, in the production of energy or whatever. So different potential paths from a societal point of view are translated in different potential paths in terms of concentration of the greenhouse gases. For instance, here you have the representation of the future condition of the carbon dioxide and the methane up to the end of the century. These are three scenarios. The purple one is a symmetry scenario, what we had in more than 10 years ago. This is what was called the A1B, the old business as usual scenario. And then in this blue one and the red one are the semi-fi scenario, RCP 4.5 and RCP 8.5. Now the business as usual scenario is this one, the RCP 8.5. What is the meaning of RCP? RCP stands for Representative Concentration Pathway. 8.5 stands for 8.5 watt per square meter difference in terms of surface radiative balance at the end of the century with respect to the pre-industrial period, 4.5 watt per square meter with respect to the pre-industrial period at the end of the current century. So this is the worst scenario. This is something that is a little bit better. Both of these scenarios are far from the 2 degrees or the 1.5 Paris Agreement you have heard maybe in the past days. But if you take a look at this time series, you can decide to run your general circulation model fully coupled, atmosphere and ocean. They are self-sustained, no boundary condition necessary. Just you can provide to the general circulation model a series of numbers representative of the different concentration we do expect in the future. So you can run your model following this path, or following this path, whatever. You have to run 100-year simulation with different radiative forcing. You provide to your model the different concentration time series at the year frequency for the main gases here. There are also other gases that are taken into account. For instance, in the CMCC experiment, also the aerosols, 3-dimensional fields are provided with a higher frequency because in this case the seasonal cycle is important, and also the ozone is provided to the model. These are all of the forcing playing a role in terms of radiative balance that we give to the model. We run the model for the entire period I've shown you before, and we obtain this result. Different projection, for instance, for the surface average temperature. You can see that in the worst case, you have an increase that is more than 4 degrees with respect to the actual value. In the best case, just few degrees. This is what you can do with the model. You can play. Obviously, these differences are not constant around the globe. The increase in temperature, the upper panel here, in the best scenario and in the worst scenario is really different also in space. There are regions that are more affected by the warming. For instance, this region here, the northern pole, is the one that is most affected by the warming, but also changes in precipitation are really different in the two scenarios. So what about tropical cyclone in this changing environment? In terms of tropical cyclone count, we do expect not only in this kind of experiment, but also in experiment idealized scenario in which we just double the carbon dioxide or quadruply the carbon dioxide to better understand the mechanisms behind. We have found, and the community agrees that the tropical cyclone count is projected to decrease in the future. This is something true at the global scale. There are small differences in the different basins, but we do expect less tropical cyclones. This is mainly because the atmosphere is going to be more stable in a warmer climate. But this is not true for the most intense cyclones, because once they are triggered, the energy available, the surface of the ocean is warmer, the energy available, the fuel is higher, and then when they start to develop, they can reach higher intensity. So less tropical cyclones are expected, but with an increasing number of super typhoons. So category 4 and category 5 are expected to be more present in the future. In terms of storm surge, putting together, this is a new approach that is the one that puts together the tropical cyclone modeling in different way, forcing hurricane models with information from general circulation model, and also putting together the information from storm surge models, etc. We can have a chain of modeling effort that gives you the final number of what we can expect in terms of sea level rise associated not only to the one induced by the warming, but also to the storm surge that is of the order of 7 meters instead of the 5 meters we have mentioned before at the beginning of this talk. Also, this is something that is going to affect significantly at least the US coast, and there are recent works that are suggesting that we have to pay more attention to the combined influence of storm surge and sea level rise in the future. In terms of extreme precipitation, we do expect, so here you have the representation, this is a really nice picture where you have the representation of the fraction of total precipitation in a year that is due to a tropical cyclone. You can see that there are regions where the precipitation is more than 40% dependent on the tropical cyclone activity. So few storms of few weeks provides 40% of the precipitation of the total that you have in the entire year. This is true over some regions, and what we do expect for the future is that also in idealized experiments where we try to disentangle the role of the carbon dioxide, so the change in the atmospheric composition with respect to the changes in the warming of the surface, we found that this is mainly the increase that we expect for the future, that is of the order of 20-25% on average, is mainly due to the increased evaporation associated to the warmer water of the ocean over certain region. And this number are a little bit higher than we would expect from the projection for the end of the century. The projection for the end of the century suggests an increase of tropical cyclone precipitation of the order of 5-20%. In the idealized experiment where we try to disentangle the role of the different component of playing a role in the determination of the increased warming of the surface of the ocean, we found that we could have also an increase of the order of 50%, but this is something that is less realistic than what we obtain running exactly the scenario you have seen before. And then if you take a look at that kind of scenario, in the worst scenario, in the RCP 8.5, taking the average of the whole CMCC-IV model representing at least category 1 tropical cyclone, you have an increase of the order of 20% of the precipitation associated to TCs. So back to the damages. This is what I have shown you, projection for the end of the century without the climate change signal. Just due from blue to red, just due to the changes in the income of the people and in the different number of people living along the coast expected for the end of the century. If we now put it together, also the signal induced by the tropical cyclone, so by the climate change signal. So the climate change signal on the tropical cyclone, how the climate change affects the tropical cyclone activity, and then you compute again this number, putting together the effect of the climate on the intensity of the tropical cyclone. This is what you obtain, and over certain region you can have an increase that is really huge and even more pronounced than what we have found in the aforementioned baseline here. So the effect is more than double over certain region. Partially there is a counter effect that is due to the reduced number we have in terms of tropical cyclone over certain region, but on average the increased intensity of the ones that still develop plays a role that goes in the plus direction. So we do expect more damages than what we had in terms of baseline, just based on the differences in the income and in the people living along the coast. So just to summarize, I hope you have somehow agree with me that the tropical cyclones are active players in our climate system. We have general circulation model now that are able to represent category 5, the most intense tropical cyclone. So we are very happy for this. It means that the interaction between tropical cyclone and climate is now realistic and will help us to understand many other mechanisms we are still trying to understand within our system. And also this will give us the possibility to better investigate the future changes we do expect in terms of tropical cyclone activity. And in a warmer climate, we expect less disease due to a more stable atmospheric condition. We expect more intense DC, more super typhoons because of increased energy at the surface of the ocean. And also we expect more precipitation associated to the tropical cyclone. This is true almost everywhere at the global scale over the tropics. And also we expect a huge increase of the costs associated to the tropical cyclone, mainly due to the not only due to the changes in the baseline, but also due to the changes in the tropical cyclone activity, mainly due to the increase in the most intense storms. That's it. Thank you.